Physicists at UC Santa Barbara have become the first to experimentally observe a quirky behavior of the quantum world. A quantum boomerang effect that occurs when particles in a disordered system are kicked out of their locations. Instead of landing elsewhere as one might expect, they turn around and come back to where they started and stop there. It's really a fundamentally quantum mechanical effect, said atomic physicist David Weld, whose lab produced the effect and documented it in a paper published in Physical Review X. There's no classical explanation for this phenomenon. The boomerang effect has its roots in a phenomenon that physicist Philip Anderson predicted roughly 60 years ago, a disorder-induced behavior called Anderson localization which inhibits transport of electrons. The disorder, according to the paper's lead author Roshan Sajjad, can be the result of imperfections in a material's atomic lattice, whether they be impurities, defects, misalignments or other disturbances. This type of disorder will keep them from basically dispersing anywhere, Sajjad said. As a result, the electrons localize instead of zipping along the lattice, turning what would otherwise be a conducting material into an insulator. They worked in momentum space, a method that evades some experimental difficulties without changing the underlying physics of the boomerang effect. In normal, position space, if you're looking for the boomerang effect, you'd give your electron some finite velocity and then look for whether it came back to the same spot, Sajjad explained. Over time and despite repeated kicks, however, average momentum returned to zero. It's just a really very fundamentally different behavior, Weld said. In a classical system, he explained, a rotor kicked in this way would respond by constantly absorbing energy from the kicks. It becomes what's called a dynamically localized state. This behavior, he said, is due to the wave-like nature of quantum systems. That chunk of stuff that you're pushing away is not only a particle, but it's also a wave, and that's a central concept of quantum mechanics, Weld explained. Because of that wave-like nature, it's subject to interference, and that interference in this system turns out to stabilize a return and dwelling at the origin. In their experiment, the researchers showed that periodic kicks exhibiting time reversal symmetry would produce the boomerang effect, BU. Up next for the Weld lab. If individual boomerang effects are cool, how much more of a party would it be to have several interacting boomerang effects? There are a lot of theories and questions about what should happen. Would interactions destroy the boomerang? Are there interesting many-body effects? Sajjad said. The other exciting thing is that we can actually use the system to study the boomerang in higher dimensions. Research on this project was also conducted by Jeremy L. Tanlimko, Hector Moss, Eber Nolasco Martinez and Ethan Q. Simmons at UCSB, Tommaso Macri at Universidade Federal do Rio Grande do Norte. Observation of the quantum boomerang effect. Physical Review X, 2022. 12, 1, doi, 10. 1103, Phys Rev X. 12. 011035 University of California, Santa Barbara. University of California, Santa Barbara. 2022, February 28. Physicists bring a once theoretical effect of quantum matter into observable reality. https://ift. tt. wyovd5e, accessed February 28, 2022. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.